This is a review of all of topic 3 in one video. Pause as needed. We're going to start with 3.1, which was all about reflections, and we're going to do the problems on page 104, 19 through 24, where it gives you different lines to reflect over. And the entire time, we're going to be using the same vertices of A, B, and C, just reflecting over different lines. So 19 and 20 were all about reflecting over the X or the Y axis, which we had very specific rules for that I have here. When we reflect over the X axis, the Y becomes negative, and when we reflect over the Y axis, the X becomes negative. So take a second, pause, and test yourself with those vertices using those two rules. All right, let's check it. In the reflection over the x-axis, the y becomes negative, check your coordinates, and in the reflection over the y-axis, the x becomes negative, check your coordinates. The one we're going to do all together is number 22, where it tells you to reflect over the line in, and the problem tells you that line in is the equation y equals 1, and we are going to use a graph to do this. So what I have done for you is I have graphed the line y equals 1, which is a horizontal line because that means that it's at the y-axis everywhere that y is 1. And I have plotted the points A, B, and C. And when you have a problem like this, it's really good to sketch a graph because if we want to reflect over this line, I just need to count the distance from each point to the line. So if I wanted to reflect point A to find A prime, I'm going to count the distance. There's 1, 2, 3, 4 units to get to our line of reflection. So then I go 4 units in the opposite direction. 1, 2, 3, 4, and right here will be A prime. I'm going to do the same thing for B and for C. So B, I'm going to count the distance to our line of reflection, which is just 1, 2, 3 units. And then I'm going to go 3 units in the opposite direction over that line. 1, 2, 3. Right here is going to be my B prime. And I'm going to do the same thing for point C. Count the distance down 1, 2, 3, 4. Go that many in the opposite direction. 1, 2, 3, 4. So my C prime will be here. And if I were to connect those, I can see that I have reflected the triangle over the line y equals 1. All right, try another one with a rule. In number 23, it asks you to reflect over line G, which was the line y equals x. And our rule for that was when you reflect over that diagonal line, you just swap your x and your y. So it goes from x comma y to y comma x. Pause and try. Now test it out. Did you just flip the x and y? That's all you needed to do. And that was reflections. We had lots of rules for them. This one was the only one that didn't have a rule. Let's move on to translations on page 112. Translations was how we moved a figure to the right or to the left, and we learned that this notation that you see here in number 5 of a translation of -4, -3. -4 means we change the x by -4, and we change the y by -3. So knowing our x is our side to side, if we're negative on the x-axis, that means we're going to the left. And if we're negative on the y-axis, that means we're going down. So we're translating this unit left 4 and down 3. Let's do that to our coordinates. We are going to subtract 4 from the x values, and we are going to subtract 3 from the y values. So we just need to do these calculations. 1 minus 4 would leave us at -3. -4 minus 3 is -7. -2 minus 4 is -6. -1 minus 3 is -4. 3 minus 4 is -1. And 1 minus 3 is -2. So now we have our new x, y, and z prime. We shifted the entire figure left 4 and down 3. We can also figure this out by looking at a figure, knowing that we start at our pre-image points and we move to our image points. So let's just pick one point. We can call it A, and let's figure out how we get from A to our image point A prime. Let's do the X shift first, and then we'll do the Y shift. So the X shift, we go over to the right. 1, 2, 3, 4, 5, 6, 7. The X shift is 7. Now let's find the Y. How many do we go down? 1, 2, 3. That would be -3 because we moved down 3. So that should be the same for every point. We can test it out. Like from D to D prime, let's see. Do we go right 7? 1, 2, 3, 4, 5, 6, 7. Do we go down 3? 1, 2, 3. Yes, we do. So that is a translation where X is 7 and Y is -3 of the figure ABCD. And you have come up with that translation rule. We also learned about composition of translations where you have more than one. And what we were learning is that you have to do the second translation first, and then you can do the first translation. Just seems a little backwards, but let's focus on those X and Y values. So if we are starting with our second translation, my starting X value would be -3. I've already moved -3, and then we combine that with a translation of +7. So that becomes -3 plus 7 for a total transformation of the X as a +4. Now time for the Y values. We look at our second Y, which is starting at -4, and then we are translating a +8. So we're -4 plus 8, which arrives us also at a +4. So if we were going to compose those translations, composition, compose, put things together as one, it would be a translation of when X 4 units, Y 4 units. Our next section was rotations, which we also had a lot of rules for. So I'm just going to remind you the rules and you can practice them. And we're going to do 19, 20, and 21 on page 122. 19 talks about a 90-degree rotation, which is where our X comma Y becomes -Y comma X. So test yourself out. How'd you do? Did you switch the X and Y and make the Y negative? In 20, it asks you for a 270-degree rotation, which means that the X comma Y becomes Y comma -X. Pause and test it out. All right, check your work. We switch the X and Y and the X becomes negative. 21 talks about a 180-degree rotation, which is where you guys learned that the X and Y stay in the same position, but they just both become negative. So test it out. Check your work. -2, -6 becomes +2, +6 as we rotate 180 degrees and completely switch what quadrant we are in. That was really all of rotations. So let's jump to symmetry. Symmetry we actually didn't have rules for. We needed to learn and use what we know about reflections and rotations to say, if I reflect or I rotate and I look exactly the same, then I have symmetry. So for number 18, we're going to find all of the transformations that can be used to map the figure onto itself, which this phrasing are also known as to make it look exactly the same. So 18, if we look at number 18, if I'm looking at this shape, I only see one thing we can do to it to transform it, but it still look exactly the same. And that's a reflection across a vertical line through the center. So that would just be one thing, a reflection across a vertical line through center. What about 19? There's some more things we can do with that. I see we could have a vertical reflection through a line through center. We could have a horizontal reflection through a line through center. And if we have those two lines of reflections, we also know that there's going to be potentially a rotation that could happen. And in this case, that could be a 180-degree rotation through center, aka it looks exactly the same upside down. If we were to spin this around, it would look exactly the same. Let's look at number 20. How many lines of symmetry does a regular 5-pointed star have? Well, we were looking at lines of symmetry of any type of polygon or shape like this. We can talk about the lines through its vertices. So we would have 1, 2, 3, 4, 5 lines of symmetry. Now, do not count just the tips, because if you just count all the way around, you're going to end up with 10. But remember that this is just one line. They're each just one line, so there's really only 5 lines of symmetry. Let's talk more about rotational symmetry. So in number 21, it's asking us to describe the rotational symmetry. And so that means the angle measures at which you could rotate it and it look exactly the same. Well, a quick trick that we found was if you could find how many lines of symmetry something has, you can find that initial angle of rotation by doing 360 degrees divided by the number of lines of symmetry. So this is a 1, 2, 3, 4, 5, 6, 7, 8-sided figure, is in an octagon. And let's find how many lines of symmetry it has. I believe it has lines through the vertices, 1, 2, 3, 4, but it also has lines through the midpoints of its segments, 5, 6, 7, 8. Notice it was an 8-sided figure and had 8 lines of symmetry. 8 lines of symmetry. So that means I can figure out that initial angle of rotation. If I do 360 divided by 8, and 360 divided by 8 is 45 degrees. So that means I can rotate it every 45 degrees and it's going to look the same. So I want to include all of the multiples of that angle, but I don't include 360 because as we discussed in class and we have learned that if you rotate something 360 degrees, it looks exactly the same. So truly that actually didn't change it at all. So if we were listing all the multiples of 45 degrees, we could rotate it 45 degrees and it would look the same. Another 45 would bring us to 90, and we're just going to keep going. Another 45 would be 135 degrees, then 180, then 225, then 270, and last but not least, 315. And we're not going to include that last one of 360 degrees. But these are all of the angles of rotation that you could rotate this figure through the center and the figure would look exactly the same. The last section we learned, is dilations, and that's not in your workbook, but we learned that dilations are either an enlargement or a reduction based on a scale factor. Enlargement, the figure got bigger; reduction, the figure got smaller. This is not a rigid motion because the size changes. And we learned to find the scale factor. It's the ratio of the image divided by the pre-image. So the length of a side of the image divided by a length of the side of the pre-image gives us that scale factor. So in this example, let's find our scale factor. The length of our image from A prime to E prime is 1, 2, 3. The length of our pre-image from A to E is 1, 2, 3, 4, 5, 6. 6. So that scale factor is going to be 1/2. We can check that this had a unit of 2. This one is a unit of 1. So yes, it was a reduction by 1/2. In this example, we can use this graph to find the vertices, which I have listed out for us already. And it tells us that we are a dilation, so we're going to change size through the center at the origin, and a scale factor of 3/5. So what we learned is this means that we need to multiply each coordinate by 3/5. So pull out your calculator and let's get to practicing. -3 times 3/5 is -1.8. You can do decimals or you can do fractions, but pay attention during your test. However, the Envision website wants you to type that in. But if I am multiplying by 3/5, first of all, that is less than 1. So this is going to be a reduction. This image is going to get smaller. And -3 times 3/5 is -1.8. That would be my x value. And now I do 4 times 3/5, and I get my y value of 2.4. And we are going to keep doing this for each coordinate, multiplying by our scale factor, and -1 times 3/5 will just be -3/5. I will leave that one as a fraction. 3 times our scale factor of 3/5 is 1.8. We need that because of -3. This would just be 3/5. Same thing, this would be 1.8. And 5 times 3/5 is 3. So these would be the vertices of my image after a dilation with a scale factor of 3/5. It should look smaller. It should be a reduction since that scale factor is less than 1. And you guys, that is everything that's going to be on your topic 3 test. You will not have a section that's just for advanced. You'll just take one part and it will all be in one assignment on Envision. There will not be any additional questions for this advanced section of this particular test.